Today's is the 7th lecture of the course and the 5th lecture on equilibrium carrier concentration. Yesterday we have started on the energy band diagram or energy band model of the semiconductor, which will give us an accurate formula for estimating the carrier concentration at any temperature in an intrinsic semiconductor. Specifically, we have discussed the first tenet of this band model, that is, what are the allowed states for electrons in a crystal. So we saw the allowed picture is something like this. You have a conduction band separated by a valence band. The bottom of the conduction band is EC, top of the valence band is EV, and here for reference you have the vacuum level. This difference EC minus EV is the energy gap. So electrons are allowed energies in this conduction band, energies in this valence band, and then below you have other bands. Now the question is, what is the distribution of the available states over these allowed energies? Now we know what are the allowed energies. Okay. So how the allowed states are distributed over energy, what is their number? So when we look at the valence band and the conduction band, the electrons which are coming here in these bands are basically coming from the 4 valence electrons of each of the atoms in the crystal. So in other words, the total number of states corresponding to, let us say, valence band would be 5 into 10 power 22 atoms per centimeter cube multiplied by 4 valence electrons corresponding to each of the atoms. These are the number of allowed states for electrons. So many states per centimeter cube. Now we want to see how these states are distributed over allowed energies. Okay. So distribution of allowed states over energy. We will just state the result from quantum mechanics. The allowed states are distributed as follows. If we take this y axis to indicate the allowed energies and the x axis to indicate the distribution of the states over energy, NE. Let us say this is EC and this is EV. Let us say the bottom of the valence band is called EB, and let us assume the top of the conduction band is called ET. So EB to EV, this is one allowed band. These 4 into 5 into 10 power 22 electrons are equal number of states. It is found that they are distributed as follows. It is something like this. The distribution function looks something like this. What does it mean? This means that if I were to take an energy interval dE somewhere here, this interval is dE. An energy interval dE at some energy E here, around this energy E. Then the number of states that I will find in this energy interval would be given by the shaded area. If I integrate the function, this particular function, over this interval, which means if I take this total area under this particular function, then that area will be equal to 4 into 5 into 10 power 22. So you have a small number of states near the edges of the band. As you move towards the middle of the band, you have a larger number of states within an energy interval. So the area here, this total area is 4 into 5 into 10 power 22 per centimeter cube. If I take 1 centimeter cube of silicon and I try to see the total number of states, they will be this many, and if these states I try to see their energy distribution, then I will find this is the energy distribution. So what is the unit of Ne? If integral Ne dE, this is Ne and this is E, so you are integrating along this. So if integral Ne dE has the unit of per centimeter cube, then it means that Ne has the unit of per centimeter cube per electron volt per energy. This point is very important to note. So the available states are not uniformly distributed over energy. That is what we find. Often when we plot functions, we plot the independent variable on the x-axis and the dependent variable on the y-axis. That is, if I were to plot Ne as a function of E, I would do something like this: Ne here and E on this axis. That is the normal procedure which we adopt, a normal convention that is adopted. So in which case the function would look something like this. This is, let us say, EB and this is EV, and this is the area that you are talking about. But here we have plotted the energy on the y-axis and the Ne on the x-axis. There are some reasons for following this convention in semiconductor physics. One is that you start from here, the allowed energy picture. Okay, you have shown the energy on the vertical axis. It is useful to align all other diagrams to this diagram. This is one reason why we choose always energy on the vertical axis while plotting the Ne, and we will later on see when we plot the Fermi-Dirac function also, we will plot that function on the x-axis, energy on the y-axis. Now there are strong reasons for using energy, for plotting energy on the y-axis. This is because intuitively for us, if you talk of potential energy, for example, a body which is at a greater height has higher potential energy. So somehow we are used to this kind of a convention when we are talking of energy. So energy is a physical quantity. We are not talking of simply some mathematical entity. It has a physical significance. So higher the location of the body, more the potential energy. So therefore it makes sense to plot energy on the y-axis. So higher and higher location means higher and higher energy. Okay, it's easy to understand, and this is the reason why, and you want to align other diagrams with this allowed energy band diagram, allowed energies diagram, and therefore the energy is plotted on the y-axis. Okay, now let us understand this particular density of states function. This is called the density of states function, Ne. What is the meaning of this function? Now we can take a simple analogy to understand this. Supposing you consider a bucket of water which is something like this. Let us assume the shape of the bucket is like this. I am assuming a two-dimensional situation. Supposing there is a bucket which is like this and you are filling it with water. say up to some height. Now supposing somebody asks you what is the amount of water at any height h, say this is height h. What is the amount of water at any height? Supposing I want to know what is the amount of water at that height. It is easy for us to know, see that it makes no sense. What is the amount of water at any height makes no sense. What makes sense is what is the amount of water within a interval dh at any h, and then it is this, the amount of water would be that. Okay. Similarly, it makes no sense to ask how many states are available at any energy E. Okay, it makes no sense because the states are distributed over energy. This is the approach that is adopted normally when we have a large number of states to deal with, okay, or a large population. Okay. So supposing you have millions of people and you want to talk about their distribution, height distribution, then it will be very difficult for you to tell at a given height h how many people are there, that is how many people have exactly height h. It is very difficult if you are talking about millions of people. Instead what you would talk about is within say 1 feet and 1 feet 1 inch, I mean sorry, let us not take 1 feet, 5 feet, 5 feet and then 5 feet 1 inch. Within this height interval how many people are there? Okay, that is what makes sense. So similarly here this is the water in bucket analogy. It makes sense only to talk about water at any height h within an interval dh. Okay. So similarly, number of states within an energy interval dE at an energy E. Okay, so you take the energy interval dE around E, only then it makes sense. That is why the unit of Ne is per centimeter cube per electron volt. I want to emphasize this point because invariably the students forget the electron volt part of this unit, and which means they have not understood the physical significance of this function. Okay, now we have shown the shape of the function and so on. What is the equation? It is important for us to know the equation. It turns out you can't have a single equation for this function. The shape is such that you can't represent this function accurately with one equation. It turns out that in practice, as we will see, what is of interest is only the function near the band edge. What is of interest is only the function near the edge of the band. So if we can approximate the shape of the function somewhere here, okay, that is sufficient for us. And it turns out a simple parabolic relationship is sufficient for representing the function near the edge of the band, and that function therefore we can write as I will read out that portion here. So this is EV, this is EB. So if I am interested in this segment is parabolic and can be written as NE equal to a constant A into square root of EV minus E. That is the function. We will write the function A in terms of various physical parameters later on. Let us come back to the conduction band. The situation in conduction band is similar to that in valence band. Okay? So the shape, the exact shape of the conduction band I will not plot here because that shape is not as simple as this. Okay? But again, as we have said, what is of interest to us is only the function near the band edge. The reason we will see later. So if I take the function near the band edge and remaining part I am showing by dotted line, I am not completing it because that shape is not really simple. This part of the function again is a parabolic function. So I can write this function as constant a into square root of e minus ec. It turns out that the constant a is slightly different for the conduction band than the valence band. So what we will do is we will use a1 to represent the constant for the conduction band, and here a2 to represent the constant associated with the valence band. The constants a1 and a2 are (8 root 2 pi into m). Let us write the constant a2 here first, mp power 3 by 2 by h square by h cube. So mp is the effective mass of holes. So for the valence band, the constant a2 depends on the effective mass of the hole. H is the Planck's constant, and the constant a1 here, it is 8 root 2 pi, and mp is replaced by mn, the effective mass of electrons. For the conduction band, the constant it depends on effective mass of electrons, mn. So that is a slight difference between a1 and a2, the effective mass of electrons and effective mass of holes. So now we know how the available states are distributed over energy. So now the final question to be answered before we can estimate the concentration of electrons, free electrons or holes and so on, is okay, if so many states are available, what fraction of these states are occupied at any temperature? Once we have that information also, then we can put everything together and get a formula. So now we come to the third tenet, that is fraction of available states occupied at any energy and temperature. Now please remember that whenever we talk of available state at any energy E, it is understood that it is within an interval dE. Okay? So states available within an energy interval dE at E. Normally within an energy interval dE, this phrase is dropped, but it is to be always remembered. Okay? So fine, supposing there is a state available at any energy interval, what fraction is occupied? This is the so-called Fermi-Dirac fraction, and this is given by the function f et is given by 1 by 1 plus exponential e minus ef by kt. It is extremely important to note that this function or this fraction is derived under equilibrium conditions. What does it mean? It means that you have assumed while deriving this fraction that if some electrons are being transferred from energy level E1 to E2 at some rate, then electrons are being transferred from E2 to E1 at the same rate. Okay, that is the meaning of equilibrium. So using these ideas, this fraction has been arrived at. Okay, there are some additional constraints also, like it is a quantum mechanical system, so that no two electrons can be present in any energy and so on. Okay, but where is the equilibrium coming? I am just telling you in this function. Now here this particular term symbol EF stands for Fermi level. So this is a Fermi Dirac fraction. It is useful to see how does this fraction look like when you plot. So again, when we plot, we will choose the energy on the y axis and the function on the x axis. So this is energy and this is the function. So the function would look something like this. If this is EF, for very high energies, for E tending to infinity, the fraction goes to 0. Okay? And for E equal to EF, let us assume t greater than 0. Okay? For E equal to EF, this is exponential of 0, this is 1, the fraction is equal to half. So for E very large, the fraction is 0, so I start from 0 here, and as I come down in energy, by the time I come to EF, this value is half. If I proceed further, as I go to E minus infinity, this term will go to 0 and the fraction will go to 1. Okay? So the maximum value of the fraction is 1. So this is 1. So I will get an exactly symmetric segment. For any one temperature. This is how the function looks like for any one temperature. How does the function look like for different temperatures? Let us look at it on a graph. So you can see here, for higher and higher temperatures, so here the curve has been plotted for intervals of 100K starting from 0K. At t equal to 0, if you see what is happening, until you come to E equal to EF, the fraction is 0, right? That is because you see here, if E is greater than EF and t is 0, t tending to 0, this is infinite, no matter what your E is, so long as it is more than EF. On the other hand, for E less than EF, for t equal to 0, it is always minus infinity. So this term is 0. Okay, this is an abrupt change. So that is what you find here. So your function comes down, and at EF it is a constant, and then it comes down again for E less than EF. Okay, so you can see that what is being plotted here is E minus EF. So E minus Ef equal to 0, so this is the Fermi level location, equivalent to Fermi level. And then when you increase the temperature in steps of 100 K, you progressively find the function shifting up. Okay. Now, what does this function indicate, this kind of shape indicate? It is very simple. What it means is, if I were to plot for t equal to 0 K, this is t equal to 0 K. And compare, all that this function says is that electrons from lower energies are moving to higher energies as you increase the temperature. So for example, here if you see below Ef, this is Ef, below Ef at t equal to 0 there were electrons, and above Ef there were no electrons, because even if there were available states, according to this the fraction occupied is 0, which means no electrons are there in those states, the states are unoccupied. Okay. When you increase the temperature, you can see that the fraction which was 0 now has become non-zero, it has, okay. Whereas here the fraction which was occupied fraction was 1, it has slightly reduced, less than 1. So that means electrons from lower energies are moving to higher energies. That is all what this function shows. Okay. So if your function temperature increases further, you will have further distortion in this. That is what we find. So more electrons are moving from lower energies to higher energies. It is important to note that this function does not necessarily say that you have an allowed energy at E. Whether there is an allowed energy state at an energy E is decided by your density of states function and allowed energy levels. If there is an allowed state, or there are states within an energy interval dE around that point, then what fraction of these states are occupied is what is given by this function at any temperature T. So to understand the shape of this function, one can actually again consider an analogy. Okay. Again you have a water in beaker analogy for this. Let us say you have a beaker which is filled with water. And now supposing we agitate this beaker and now try to see how the surface of the beaker is, the surface of the water, not the beaker, surface of the water in the beaker is. Okay. So there is an animation to show this. So here the top of the water surface is calm, okay, so no agitation. Now let us say I agitate the beaker. So you find a disturbance, and what is happening there is some amount of water from below the surface is going above the surface in some place, and some other place there is a void from where the water is transferred. You increase the agitation, there is more likelihood that you will find water above the top surface corresponding to the calm situation. Okay. And you increase this agitation even more. Okay. Let me show you the mean surface here, and this is the agitated picture. Okay. So what we are saying here is, if this is the picture when no agitation is present, when agitation is present it would be something like this, something like this. So water from here has gone there. Now increase the agitation, it could be something like this. If I were to now plot, I replace this energy by height. and instead of the Fermi level I call this as mean top surface of the liquid. Mean top surface of water, this location. And what I am plotting here is the fraction of the beaker volume occupied as a function of height and agitation. So, fraction of the beaker volume that is occupied as a function of agitation, let us say height first, because there was E first, so E is analogous to height. So, F stands for fraction of beaker volume occupied. Then in fact you will have a picture something like this, where this is increasing agitation. Your plot would look something like this. So, this is for 0 agitation, the red line is for 0 agitation. So, when there is 0 agitation, your surface, water surface is like this, and let us say this is height h naught, this is h naught. So, above this h naught you have no water, and below h naught the entire beaker volume is occupied with water. So, the fraction of beaker volume occupied is 1 below h naught, above h naught it is 0. Okay, so, this is no agitation, the red line is no agitation, that is the reference. As you increase agitation, you find some water above that surface, and that therefore the fraction of water present, okay, is non-zero above the surface. But you go higher and higher in height, definitely the amount of water, probability of finding water is going to be less and less. Okay. If you increase agitation, you are likely to find more water, okay, above height h. So, this is an analogy where the water in the beaker is analogous to electrons, the beaker volume is analogous to the allowed energies, the height is analogous to the energy, okay. Agitation is analogous to temperature, and the fraction of beaker volume is analogous to the fraction of occupied states. And finally, what is very important is this mean top surface is analogous to the Fermi level. The mean top surface of water is analogous to the Fermi level. Okay. So, this kind of analogies help us to appreciate the physical significance of these ideas, okay, which are sometimes very abstract. Now, let us focus on this EF a little bit more. How do we interpret EF? There are two ways of interpreting EF. One is in terms of the behavior at t equal to 0. In terms of the behavior at t equal to 0, we can say, so physical significance of EF. In terms of the t is equal to 0 behavior, we can say it is that level above which no allowed level is occupied and below which all allowed levels are occupied. Okay? So, it is that energy below which all allowed levels are occupied. And I can simply write, I can replace below by above here, and here occupied by unoccupied. So it is the energy above which all allowed levels are unoccupied, or none of the allowed levels is occupied. It is the same thing. This is one way of interpreting EF. What is the meaning of EF? At t equal to 0, this is very important. This interpretation is valid for t equal to 0. So let us look at that function. So this is at t equal to 0. You can see that the function is 0 until you come to EF, and suddenly it changes to 1. Alternately, you can interpret in terms of the behavior for t greater than 0. So at t greater than 0, if there is an allowed level at E equal to EF, then exactly half of the number of states which are occupied, half of the number of states which are available will be occupied. Exactly half of the states will be occupied at E equal to EF at t greater than 0k. So it is energy at which exactly half of the available states are occupied at t greater than 0. Now we will see when we take up p-n junctions that the Fermi level has other physical significances also. So it is a very important parameter in the analysis of electronic systems under equilibrium conditions. So now we can put our information together, namely the allowed energy states, the fraction of states occupied at any energy E, and the density of states function, and we can try to derive an equation for the carrier concentration, the intrinsic concentration. Now when we do that, or rather before we do that, let us discuss one approximation of this function that is often used to derive simple formulae, and that is called a Boltzmann approximation of this function. So Boltzmann approximation. This is valid for E minus EF by KT greater than 3 or less than minus 3. E minus EF by KT is either greater than 3 or less than minus 3. That is, E is above EF by more than 3 times KT, or E is below EF by more than 3 times KT. In such a case, this approximation holds. Now what happens for this case? If E minus EF by KT is more than 3, then this term is much larger than 1, and therefore you can neglect 1, and your function will become, so Fe comma t is approximately equal to exponential of E minus EF by KT with a negative sign. For E minus EF greater than 3 times KT. Alternately, for E minus EF less than 3 times KT, if E minus less than minus 3 times KT, if E is less than EF by more than 3 times KT, then this is exponential of minus 3 or exponential of minus of a quantity more than 3. Then this quantity becomes much less than 1. If that is the case, you know that 1 by 1 plus x, where x is much less than 1, is 1 minus x. 1 by 1 plus x is approximately equal to 1 minus x for x much less than 1. You are familiar with this approximation. So using the same approximation we can write f of E comma t is approximately equal to 1 minus exponential of E minus EF by KT. 1 minus this same x, where E minus EF is less than minus 3 times KT, that is important. So if you want to compare the Fermi-Dirac function and the Boltzmann function, distribution function, this is called the Boltzmann distribution function. Okay, then how will they look like? It would be something like this. Let us do it for any one temperature. So this is EF, this is E, and this is F, the function F. If this is the Fermi-Dirac function, this is 0 and this is 1. This is half. Now if you were to sketch the Boltzmann approximation, it would be something like this. It will almost be the same as this function until you come to 3 times KT above EF, and there it will deviate and it will go like this. The lower segment will be again something like this. So let us mark the interval. This is EF and this is 3 times KT below EF. So this interval that interval is, or this interval, these two intervals are 3 times KT. So the Fermi-Dirac function and Boltzmann function will be almost the same. So it turns out many times, or most of the times, when we use this function, Fermi-Dirac function, we use it in the range where the Boltzmann approximation is valid. Okay. Now one might ask that these are such simple approximations, so why does it need a Boltzmann to tell you that you can use this? The point is, what we have discussed is the mathematical method of deriving the Boltzmann function. Now what is the physical significance of that? What exactly has changed? Which assumptions have been modified? Okay, there are some assumptions which have been used to derive the Fermi-Dirac function. Now which of these functions is modified to derive the Boltzmann function? It turns out that the particular assumption that is modified is that the Fermi-Dirac function derivation assumes that no two electrons can occupy the same energy, whereas Boltzmann derivation assumes that any number of electrons can occupy the same energy. Okay, so that is a physical difference between the two. Now let us discuss the estimation of the concentration. So formula for Ni. So we can write Ni as the number of electrons in the conduction band at any temperature. Ni is the number of electrons in the conduction band at any temperature. So which means Ni is equal to integral Ec to Et so Ec is this level, bottom of the conduction band, and Et is the top of the conduction band, somewhere here. How many electrons are there? So integral the available states function. So within energy interval dE at E, the number of states available is Ne into dE. Out of this, the fraction E comma T is occupied. So you integrate this over the conduction band, you should get the intrinsic concentration. Okay? So graphically, if you want to represent this, it would be something like this. So this is your Ne function. This is your Ne into dE. And a fraction of this is occupied because you have the Fermi Dirac fraction going something like that. So this is Fe. As of now, if I want to sketch this function, I should know where the Fermi level is. I do not know. Okay? So I will assume it is somewhere, but I just want to show the fraction function. So here all the three aspects have been shown in this diagram: the allowed energy levels, the distribution of available states over energy, and the fraction of states. So you multiply, so this is the available states, multiply this by this fraction, which means what is shown in this red portion, that is the number of electrons in the energy interval dE. So that shaded area here shows within energy interval dE how many electrons are there, because ratio of this area, red area, to this white area over this interval dE is actually the fraction that is occupied. So that is this term, and now you integrate, you will get the total number of electrons. How does this function look like? Multiplication of Ne into f of E, it looks something like this. It looks something like this, and that area is the integral. So the red, the boundary of this red, this is Ne into F E at any temperature, and this area is Ni. Fermi level is somewhere below. This is EC, this is EC. Fermi level is somewhere below here. We right now you do not know where exactly it is. That we have to estimate. Now you can substitute the various terms and your function will look something like this. So this is equal to integral EC to ET. So NE is of the form A1 square root of E minus EC. F of E is 1 by 1 plus exponential E minus EF by KT dE. You have to perform this integration. There is no way you can get a simple closed form equation for this general limits EC and ET. So one uses some approximations. So first thing is the Boltzmann approximation. You use the Boltzmann approximation to this Fermi Dirac function, because one can show that your EF will be below EC by more than 3 times KT. Now you do not know this in advance, okay? But from intuitive reasoning one can know this. Normally the way to check such approximations is you make the approximation, derive the result, and from the result you try to see whether your EF has turned out to be below EC by more than 3 times KT. If that is so, then your approximation is valid. So you make an approximation, derive the result, then cross check, okay, whether the result is in conformity with the assumption or does it contradict the assumption. So first approximation is the Boltzmann approximation. The next approximation is you replace ET by infinity. Replace ET, the top of the conduction band, by infinity. Why does this work? This works because this function f of ET rapidly drops to 0, okay, much before you reach your top of the conduction band. Your top of the conduction band will be somewhere here. So it does not matter whether you are taking the limit up to ET or to infinity. The area under this is not going to change, it has already dropped to 0 much before you reach ET, okay. So let us write the two approximations. One, ET tending to infinity. Second, Boltzmann approximation. And the third is this formula that we have written already. There is also an approximation that has been used, that is the parabolic density of states approximation, okay. The actual function, density of states function, is more complex. We are using a parabolic density of states approximation. Parabolic density of states. Under these 3 approximations, you can get a very simple result of this. And what does it look like? It looks like this. Ni is equal to two into 2 pi mn kt by h square whole power 3 by 2 into exponential of EC minus EF by KT with a negative sign. Okay, so you are basically substituting for A1 here, right? And of course you are making some substitutions for evaluating the integral. So if you, for example, you make a substitution E minus EC is some variable, then your lower limit will become 0. Upper limit is already infinity. Okay. So how the integral looks like under these approximations, you do it as an exercise. Evaluation of the integral is, I am not asking you to do that because that will involve some higher level of mathematics, but at least you can write then in the simplest possible form under these approximations. Okay, and then one will find that this is the relation. In the next class, we shall interpret this formula for Ni physically. We will derive a similar formula for the whole concentration, that is Pi, and then using the fact that Ni is equal to Pi, we will derive an equation for the Fermi level.